Some of the things that we also regard is the last step in this gas law is Amonton's law, sometimes called Gay-Lussac, but we try and use Amonton instead. And this is looking at the pressure related to the temperature. So if the pressure of a gas is kept at a constant volume, then if you change that pressure, then the temperature increases. So it's discovered empirically between around about 1700s. And the kinetic molecular theory basically states that the temperature is this measure of the average kinetic energy. So as the kinetic energy increases, which is as the temperature increases, the particles collide with container more rapidly and therefore increase the pressure. So all of these laws can be combined. We've got Boyle's law, which is at constant temperature, P1 V1 equals a constant, or P1 V1 equals P2 V2. Charles' law at constant pressure gives you V1 over T1, V2 over T2, and Amonton's law at constant volume. So you can see all of these work out to be a constant. So you go, well, hey, if they're all a constant, let's combine them. So we combine them to form the combined gas equation. P1 V1 over T1 equals P2 V2 over T2. So provided that your volumes have the same units and that your temperatures are in Kelvin and that your pressures have the same units, you can use this law to compare between what happens at one pressure or at one volume and what happens at another pressure or another volume. And this is also assuming that the number and type of particles don't change. So you're not adding gas or removing gas, it's just the same volume, same number of particles which are then changed. So using the data that Charles and Boyle had, Gay-Lussac actually figured out another volume to temperature relationship. That was the same as the Amonton's law. But remember, Amonton was before this. He was like 1700, whereas Gay-Lussac was 1787. So he kind of reinvented it. But he did invent something a bit more interesting, this law of combining volumes, where the ratio of the volumes of the gas consumed or produced in a chemical reaction is equal to the ratio of simple whole numbers. This is one of the things that actually led to the theory of atoms. So 2 volumes of carbon monoxide and 1 volume of oxygen gives you 2 volumes of carbon dioxide. Brilliant, you say. Excellent. That's what led to Avogadro's law, which gives you the idea of instead of having volumes, you have numbers of molecules. So you get Avogadro's number. And this means that regardless of the chemical nature of the gas, you have the volume is proportional to the number of molecules. And this means that you have a molecular volume or a molar volume. And this holds really only at low pressure, so at high pressures again, because the kinetic molecular theory states that particles take up little space, but when you get to high pressures, then the particles actually take up quite a significant amount of space compared to the volume of the gas. But for this low pressures, this works, which means that you can combine that combined gas equation and Avogadro's law to get the ideal gas equation. And you notice I haven't given any examples yet. That's because I like to work through basically from the ideal gas equation, because if you work from ideal gas equation and just eliminate any of your extra variables, you never go wrong. So the constant that they use is R, called the universal gas constant. So when your pressure is in kilopascals, your temperature is in Kelvin, and you have your volume in litres, your constant is 8.314 joules per Kelvin per mole. And that's your universal gas constant. And we'll do a couple of pracs that look at that. So an example. In this one here, we have a certain amount of hydrogen gas in a fixed volume. The temperature of the gas is 27 degrees. What is the pressure? So here you say, okay, well, let's just plug it in. The pressure, don't know, but the volume is 0.25 litres, number of moles, 0.3, 8.314, and you've got your temperature in Kelvin. Plug it in, you get a pressure of 3,000 kilopascals. So making sure that you do all these conversions. Just to give you an idea of how everything works, this is originally Boyle who came up with the pressure-volume relationship. Charles then came up with the volume-temperature relationship. Amonton, as I said, was before Gay-Lussac, 1700s. He came up with the pressure-temperature relationship. Gay-Lussac came up with the volume relationship, and Lord Kelvin came up with this description. So even though Kelvin is basing his data on Charles, it wasn't until they got to here that they actually introduced the Kelvin. Quite interesting, really. And Avogadro, basing his work on Gay-Lussac's, produced Avogadro's number, particularly for gases. So rather than convert these various units of pressure and temperature and changing everything around, we use two sets of standard conditions: standard temperature and pressure and standard lab conditions. So STP is at 0 degrees, always remember that, 0, and standard lab conditions are 25 degrees. So I just want to give you a couple of ways to use the gas laws, and the way that I prefer is to use the ideal gas law. And I'm going to give you a couple of examples on how to do this. Now, normally you can just identify a problem as either a Charles or a Boyle or an Avogadro type problem and then use the appropriate law. But if you use the ideal gas law, then you can cancel out all the redundant terms and you don't need to use those individual things. So the idea, I'll give you two tips. One, put all the variables on one side of the equation and then constants on the other, and then ensure all your variables and constants have the right units so that your ratio of pressures or volumes, the units may cancel, and then they don't need to be converted. So sometimes you need to have your pressures and your volumes in the right unit. Other times, if they're in the same units, you can cancel them out. The thing to remember is that the temperature must always be in Kelvin. So the example we've got here is ammonia gas. Has a volume of 7 mils at a pressure of 1.68 atm, and the gas are compressed about 3 times to 2.7 mils at constant temperature. Find out what to do to calculate the final pressure. So you could do this and go, well, I could do this, it's got constant temperature and I'm only changing pressure and volume, so that's actually just the Boyle's law. So I could use the Boyle's law equation, but I'm going to use the ideal gas equation to do it this way. So first I list the variables. Where are we going? Got pressure and volume, P1, V1, P2, V2, and then I can use the ideal gas law, and I use R in terms of the atmospheres this time instead of E in terms of kilopascals, because my pressure is in atmospheres. And because I'm lazy and I don't want to have to change it, I use my gas constant in this form, so 0.08206 litres atmospheres per Kelvin mole. And what are the variables that change? PV, nRT changes the same. So we write out our ideal gas law so that the things that change are on one side, the things that stay the same are on the other side. So we have P1 V1 equals nRT equals P2 V2, which is Boyle's law. In any case, we know that these remain constant and we don't have to worry about them. Pressure in one term is 1.68, volume 7, so we'll put them in. Rearrange, so we've got pressure 2 on one side and pressure 1 on the other, so 7 over 2.3. So remembering we're compressing it, so it's about 3 times more compressed, so we expect our pressure to go up, which is what it does. Now, reality check. I always put this in a problem solving because you've got to check it. Does it make sense? The volume decreased, so the pressure increased, and the calculated pressure is 4.4 atmosphere. Remembering that gases don't behave ideally above 1 atmosphere, so therefore if we measured the pressure, it might differ slightly. We'll come back to that at another time. Another example, diborane gas, B2H6. It has a pressure of 345 torr, okay? Torr, what was that? That's the same as bar, okay? It's also the same as 760 milligrams mercury. So what we can do is say, okay, well, in this case we've got our pressure in torr, but we've still got our gas constant in atmospheres. So what are we going to do? What are the things that change? Pressure changes, volume changes, and our temperature changes, all 3. So we could use the combined gas law, knowing that our number of molecules doesn't change. But we're going to use the ideal gas law. Collect everything that changes, P, V, and T on one side, and collect it on the other side. So collect them all, rearrange, and you'll see we get to the combined gas law. In this case, we're using our torr in the same variable, so because remember that gases, when you change them, it's just a ratio. So in this case, we're looking at a ratio of pressures. Now, if in this case we were looking for the pressure and we only have one pressure in torr, we might have to change it into atmospheres so that it was consistent with the gas constant. Working through, we put in our temperature. Remember, it's in Kelvin. Did we put it in Kelvin here? We had it in degrees, but we converted to Kelvin. So we put it in Kelvin and we get a volume. And then we go, okay, is that correct? 3 litres. What did we start with? We started with a volume of 3.4, but we're increasing pressure. So we expect for the volume to, if you're increasing the pressure, your volume's going to decrease, except for the fact you're also increasing your temperature. So if you're increasing your temperature, your volume increases. So you've got two competing things, and you go, does that work? Yeah, okay. It works. Third example. Sample with argon gas at a temperature of 13 and a pressure of 58, heated, and the pressure changes. What's the change in volume? So again, we're going to use the same thing, but this time we're going to set it up in state 1 and state 2 because we know that there's a change in volume. We know that the number of moles is the same, and we also have to change our pressure into atmospheres in this case because we want to look at the change in volume, and we're not given anything else. We know that we have to include the ideal gas law, we need to include the number of moles. So again, we've got this in terms of atmospheres. So what I've done is I've changed the pressure into atmospheres. For 568 torr is about 0.7 atmospheres. 897, that's more than an atmosphere, so 1.18 atmospheres. So we want to find V1, and so we rearrange our equation for V1 and we rearrange it for V2. You notice here we didn't actually have volume. What we're asked is to find a change in volume, and that is why we had to convert our pressures into atmospheres, because we needed to actually find the volume each time. So volume 1, we use N1 RT over P1, which gives us 11 litres. Volume 2 gives us 8 litres. The change in volume is the difference between them. The change in volume is negative, and the volume decreases. You look at it and you go, is that right? Well, what happened to the pressure? The pressure increased, so the volume has to decrease, even though our temperature did go up in this case. And you see that in this case, the pressures had to be converted to atmospheres because each volume is found separately, and the conversion factors then don't cancel. So for you, go and check and see if you can find out these things. Find the volume for this amount of gas, particles, and work through those solutions. Good luck.